Welcome to Quantum Curious, and in today's video, I'm going to discuss another property related to coherent states. So in the previous lecture, we learned about different properties of coherent states that what are the coherent states as they are the eigenstates of annihilation operator, and we saw that they are minimum uncertainty states. And these states have properties more related to classical states, and that is why they are usually called quasi-classical states. So we also saw that they have a pretty constant phase throughout the propagation as similar to the classical states, and they have fluctuation of uh, photon number, and these fluctuations follow the uh, Poisson distribution. So that is why they are usually called Poisson distributed states. So in today's video, I'm going to discuss how we can create or generate coherent states through different kind of states like fog states or uh, vacuum states. And the operator that is going to play a key role in this generation is called displacement operator. So let's jump into this discussion. So we know that the photon number state can be written in terms of the vacuum state through the application of successive creation operators. And we also know that coherent states can be written in terms of the fog state. And combining these two equations, we can write coherent states in terms of the vacuum states. So we know that this fraction is going to sum to be exponential, and we could write uh, this sum as an exponential of alpha a dagger applying on vacuum state and generating coherent states. So in order to make this operator identity exponential, we have to introduce another uh, another kind of exponential, and let's see how we can do this. So we know that the action of annihilation operator on vacuum state is going to annihilate it. So we can introduce the exponential of annihilation operator in order to make this quantity or this operator identity or exponential operator and unitary in order to be it physically. We can introduce this exponential operator. So combining this exponential operator with it, we uh, are going to have this. So still, it is not a single operator. It is a product of operators. So in order to make it single operator, we are going to use Campbell-Baker cost of operator identities. So we could write the product of operator as single operator using this identity, and we are going to evaluate first the commutator of these two operators. So the commutator of these two operators is just a complex number that is alpha mod square, and putting these values in place of A and B, we could write a coherent state in terms of a single operator and vacuum state. So these two exponentials are just constant, and they are going to cancel each other due to they have opposite signs. And uh, we could write the coherent states as uh, in terms of the uh, vacuum state, and this operator is a displacement operator, and it has this particular uh, name because it displaced the vacuum state in phase space, and the resulting displaced state is a coherent state. And this could be achieved physically by a beam splitter, and the beam splitter is going to be very unbalanced beam splitter, as it is as it has to be a beam splitter with high transmittivity, and one port will be going to have vacuum state, and another port of beam splitter will be going to have a highly intensity, a classical arc or a classical state with a very high intensity, and they will interfere in the beam splitter, and the output will be a displaced state, also called the coherent state. So this is how we can realize the uh, physical through the so this is we can how we can realize the physical experiment of displacement and the physical realization of this displacement operator. So we could write the coherent state as the displaced state or displaced vacuum state, and we have achieved this goal through the displacement operator. So it has some peculiar properties, like it is unitary, as every physical realizable operator should be denoted by a unitary operator, and the action of these operator on creation and annihilation operator is going to be have a addition of a complex number. And we could write the action of successively applied displacement operators through the use of Campbell-Baker-Host of operator identity, as the product of two operators could be written as the sum and the phase value. And this phase value is showing that these two operators are non-commutative. So again, we could use the coherent state as the representation of different quantum states, as we have used previously, that we could write we could write the different quantum states in terms of Fock states. But now we are going to write the Fock states in terms of the coherent states. So we could write this as uh, a number of state can be represented as an integral over coherent states using this, and we want to evaluate this inner product, as it is an overlap between coherent states and Fock state. So we know that we could write the Fock state or the coherent state in terms of the Fock state. So overlapping these, we could get a complex number. And putting this, we have the representation of the Fock state in terms of the coherent states. So next, we know that we could use the coherent states as the basis to write another quantum states, and we know that uh, a set of bases should follow the completeness relation in order to be physically realizable, or in order to be valid basis set. So let's see whether the coherent states also follow these kind of identity or completeness relation. So we have coherent states in terms of Fock states, and we could write their outer product using cat and bra notation, and taking integral on both sides, we end up with this expression. So we want to evaluate this integral. So we could use this integral result, and we know that the Fock states follow the completeness relation, and we end up with a result that the coherent states also follow this completeness relation. So these are valid basis set, and we could write the quantum states, different quantum state in terms of the coherent states. So next, see the orthogonality condition of these coherent states. So we know that the different bases or bases with different eigenvalues are orthogonal to each other. So let's see whether what is the case for these coherent states. So we have different coherent states, and we could take their inner product by writing them in terms of Fock states, and we are going to have this. So evaluating this sum, we are going to have this. So you could see that the coherent states are not going to be, uh, or their inner product is not going to be zero, or it is not zero unless alpha and beta are different from each other. So this is very peculiar property of the coherent states, and it is because they form the over complete set of bases in Hilbert space. So we have more coherent states that we need uh, in order to write quantum state in terms of the coherent in terms of a coherent states. So that is why they are not going to orthogonal to each other, and sometimes they are dependent on each other. So this is a very different property from other states that we have seen so far. So in today's video, we saw that what are displacement operator and how can we generate the coherent state in from the action of these operator. And then we saw different properties of the displacement operator, like unitary. It is a unitary operator, and we could try the product of different displacement operator as a single operator, but with a phase value. And then we saw the representation of Fock state in terms of coherent states, and we deduce very important and peculiar properties of coherent states, like they are not orthogonal to each other and they form the over complete set, and but they usually follow the valid basis set condition, like they follow the completeness relation. So that is for today.